Hi. I'm sure you have seen this before. It's a so-called Möbius strip. It is an astonishing entity with only one side, one surface, one edge. A similarly astounding object is Klein's bottle, a three-dimensional object with only one surface. To mathematically describe the properties of such objects and to compare them with others, that's a task for topology. Here we are not going to deal further with the topological features of such two- or three-dimensional objects, but with the topological properties of n-dimensional networks. Like, well, like that one. How can we do this? In topology, two objects are homeomorphic, or simply topologically identical, if you can transform one into the other by simple deformations like stretching or bending, without breaking any connections. This may be an interesting problem when we want to compare two networks or graphs.
Let's have a look at these four networks. One of them is not equivalent or homeomorphic to the others. We learned already that there is a convenient way to represent a graph as adjacency matrix. Here are the adjacency matrices for the four graphs we want to compare. They represent all connections in each of our graphs, independent of any layouts, graphical arrangement, stretchings or bendings. Again, the question is, which is different? For comparison, we simply overlay the adjacency matrices, here those of graph 1 and 4. We see that they are obviously identical. When we do the same with the matrices of graphs 1 and 3, we see that they are also identical. When we do it for graphs 1 and 2, we immediately see that they differ in two positions, which both represent the connection between nodes P and Q. Remember that when we deal with an undirected graph, as we have here, the adjacency matrices are symmetrical and the connection between node P and Q is the same as that of Q and P. Here we see in the original graphs that the connection between P and Q was missing in graph 2 only. Of course, in such a simple example, you could have simply first of all counted the nodes in each graph, which are 6 in all of them. Next, the number of edges, and find that one is missing in graph 2 only. To learn more about the difference, you could have counted the number of edges of each node and would have found that nodes P and Q have 3 edges incident to each of them in all graphs except of graph 2. As we have seen, if we add to graph 2 an edge between nodes P and Q, the resulting graph 2' is homeomorphic to graph 1. But simple counting of nodes and edges may not help if we, for instance, change the positions of nodes P and Q with nodes R and T. The resulting graph 5 has the same number of nodes and edges as graph 1, but we added the new edge between nodes R and T, and that of P and Q is still missing. As a consequence, we see quite a number of differences between graphs 1 and 5 when we overlay their adjacency matrices.
We mentioned a number of edges at one node, or as we may say, incident to one node. This number is called the degree of this node, often represented by the letter K. We see that in this case, the degree ranges between 1 and 4.
The degree K of each node can also be deduced easily from the adjacency matrix as sum of the respective column or row when we have an undirected graph, as in this case.
Just to mention at this point, if we have a directed graph, we differentiate between incoming and outgoing edges and correspondingly between in degree and the out degree of a node, which you can separately infer from the columns or the rows of the adjacency matrix respectively. But let's have another look at this graph. There is only one node with degree just 1, and one with 2, and one with 4. But 3 have the degree 3. Obviously, the degree is unevenly distributed around an average value. Here it is about 2.7. But this is worth to have a closer look at.
Let's consider such a graph of 20 nodes. Imagine these nodes would be little magnets. Now we throw in 40 iron rods which connect randomly node pairs. Next we count the degree of each node. The degrees range from 1 to 6. But what is their distribution? We notice that the degree 4 is the most frequent one. This corresponds to what you may get by a simple calculation. Each of the 40 edges has 2 ends, so we have altogether 80 edge endings that distribute amongst 20 nodes, which means 4 per node. And this is what we generally observe. Each random network has such a degree distribution around an average value, which you can calculate when you know the number of edges and nodes in this network. But what you actually observe in many real networks is something else. Here you see that the majority of nodes has a very low degree, and the number of nodes is continuously decreasing with increasing degree. Such a network looks like this, and we call it a scale-free network. The reason for this we'll see in a minute. But for this we have to introduce a bit of mathematics. Here you see the formula that describes the degree distribution on a random graph. It is a so-called Poisson distribution. It just tells us that the probability pk to find a node with a certain degree, or the frequency with which a certain node degree occurs, is proportional to a function where the average degree appears twice, once as exponent of an e function, and again powered by the degree itself. But how does it look like in the case of the scale-free network? Here, the probability to find a node of degree k follows a power law, which means that k is raised by the power of a negative constant minus gamma. That has an interesting formal consequence. When we logarithmize this proportionality, we see that log pk and log k are in a linear relationship, with minus gamma as the slope. That is, when we put the degree distribution of the former diagram into a double logarithmic scale, we get a declining straight line. This is often used as an empirical measure to determine whether a given network is of scale-free nature. With this linear representation, it is also easier to comprehend the term scale-freeness. If we scale the degree distribution by a constant factor c, this is also raised by the power of minus gamma, which does not change the proportionality with the degree k itself. Or in the double logarithmic scale, the distribution of log k is still a linear one, just that the straight line is subject to a parallel translation, shifted by this constant value. That's what we understand as a scale-free network or scale-invariant network. The reason why we consider these scale-free networks in such a detail is that they have some more interesting properties. As we have seen before, one of their characteristics is that most of the nodes have a low connectivity, as the green nodes here with degree 1 or 2. On the other side, there are a few highly connected nodes, the red ones. We call them hubs. These hubs count for a particularly interesting feature of scale-free networks, the small world property.
As we will explain later in greater detail, these hubs are responsible that the average path length, that is the connection between 2 nodes in the network is relatively short, shorter than in a random network. That was demonstrated in 1967 by an interesting experiment. 50 randomly picked individuals in Kansas and Nebraska were asked to send a letter to a broker in Cambridge, Massachusetts. They did not know this person at all, they just knew his location. They were just asked to hand the letter over to another person, of which they assumed that he or she would be closer to the target person, either by location or by profession or any other criteria. Consider that we speak about a network of about 200 million nodes, the number of citizens in the United States at that time. The interesting outcome was that on average, the letter arrived after 6 steps. How can that be?
Let's compare these two networks, or graphs, which represent two kinds of extremes. On the left, we have a bush-like structure, whereas on the right, we have a linear arrangement of nodes. This difference is reflected by the node degrees. The bush-like graph has one hub of degree 6 and 6 peripheral nodes of degree 1, whereas in the right linear structure all nodes have the degree 2 except of the 2 end nodes with a degree 1. Otherwise, both networks have the same number of nodes, 7, or edges, 6, and even identical average degrees of 1.7. The difference between both graphs, which is the presence of a hub node in the bush network, causes much shorter passes between any pair of nodes here than in the linear arrangement. The average path lengths are 1.52 versus 2.67. These are the values for 7 nodes in these structures. Preserving the structures of both graphs, bush-like versus linear, but increasing the number of nodes makes this difference even more prominent. When we triple the number to 21, we have 1.9 versus 7.33. And for 100 nodes, we end up with an average shortest path length of 1.998 versus 33.67. You see that in the bush-like structure with a hub node, we approach a boundary of value 2. That is understandable, since the few short passes of length 1 between the hub and the peripheral nodes get more and more dominated by the many passes between the peripheral nodes of length 2. But there is no shortest path between any node pair that is longer than 2. On the other side, the average length of the all shortest passes increases continuously with the number of nodes in the linear network.
There is one more important property of scale-free networks connected with the presence of hub nodes. They are more robust than other types of networks. Randomly picking and erasing one node from the network has little impact on a scale-free network unless you hit, by chance, such a hub. So, is that all mere theory, or are there any real examples? There are, although frequently not perfect. Like this one, the electricity network of the United States is one such example. The double logarithmic diagram shows a clear linear relationship. The internet may be of this type as well, as are social media networks. Extremely short average path lengths have been computed, for instance, for the Twitter network. What about biological networks? Let's have a look at the protein-protein interaction network of yeast. Independent of the source for the underlying data, they show a linear dependency in the double logarithmic plot, although not perfect as in most real-world networks. There was a time when people believed that all biological networks should be scale-free. And there was even a nice evolutionary theory behind, that of preferential attachment. Whenever a new node appears in the network, for instance due to gene duplication, it is much more likely that it is connected to an already highly connected other node, a hub, than to any other node. Today, we know that not all biological networks are scale-free, and that sometimes apparent scale-freeness is just the result of incomplete knowledge about the network. Occasionally, our view on a presumed scale-free network may just be the rightmost part of a Poisson distribution, as in this case. Maybe the low connected nodes in our preliminarily constructed network had many more connections, as was discovered later. More low connected nodes were discovered later, and apparent hubs were first overestimated, since they raised the attention of the scientific community for some time, like the tumor suppressor P53, when it became the molecular of the year in the 90s. Anyway, the small world concept has been empirically proven in many contexts, in biological as well as in social networks, and the existence of very shortest passes is of very practical impact for our life. Today I have introduced a new keyword, preferential attachment. Is there anything like preferences in a network? Maybe not just resulting in hubs, but in node clusters? That's something we will deal with next time. See you then.